Alright, London dispersion forces are a specific type of van der Waals force. So here we have helium, which we don't consider to be a polar atom, right? No atoms by themselves are polar, but even if I think about just a helium atom, it's got 2 electrons, right? And even though we generally would probably think about the electrons being on opposite sides of the nucleus, in fact, it's possible for any split second that the electrons are closer to each other than they are, and they're not equally spaced apart. And what that does is it sets up a temporary dipole. But as quickly as it forms, it also comes apart, right? Because the electrons are always moving. So it's an instantaneous, very weak intermolecular force. So for that one instance, the atom or the molecule can become polar. And if I have another helium beside it that also has dipole forces, it can, or even if it doesn't have the London dispersion force, it can cause the other molecule or another atom to polarize. It can cause the electrons to shift, right, and cause the other one to polarize. So one becomes slightly polar with this skewing of electrons, can cause an adjacent one to also become skewed. So we have these instantaneous dipole, and we call it an induced dipole. So you get a dipole in one, it induces a dipole in an adjacent one. So these forces are present in all molecules. Doesn't matter whether they are polar or nonpolar. So if you ask what kind of van der Waals forces exist in nonpolar molecules, the only thing that they would have is London dispersion forces. Okay, they're not polar. Okay. So we call the tendency of an electron cloud to distort in this way polarizability. So can I polarize a molecule by causing the electrons to skew? So the things that affect London dispersion forces are the shape of the molecule, right? So here I have basically the same formula, and here this pentane is more linear. Here it's more circular. And because this has more surface area and more electrons on the surface, it tends to have slightly greater London dispersion forces. Now the other thing that you will often see, and I almost referred to this earlier, is that as the molecular weight, so I have all halogens, right? And as the molecular weight increase, we also see an increase in boiling point. So what's important here, though, is it's not the molecular weight that causes the increase in boiling point, it's the number of electrons. So as I go down this row, I'm adding a whole nother shell of electrons, right? So it's the increase in the number of electrons. The more electrons I have, the more they can skew. So on the AP exam, if there's a question about what causes a higher boiling point, you can't say iodine has a higher boiling point than chlorine because it's got a higher molecular weight. You have to say it's because it has more electrons. Okay, so it's all about larger electron clouds, which are easier to polarize. So which is going to have a greater effect, a dipole-dipole or a dispersion force? So if two molecules are about the same size and shape, dipole-dipoles will be stronger. But if you have a really large molecule and another that's small, then you might have dispersion forces that dominate and dictate the physical properties. But usually the dipoles are going to be greater than the dispersion forces. Okay, so here we have, let's just focus on the blue line first. Here we have increase in molecular weight. We have, in all cases, we have a tetrahedron shape. We have carbon and then silicon. So in all cases, this is the same group in the periodic table, carbon, silicon, germanium, and tin. And as I increase molecular weight, I'm also increasing electrons, and I have a predictable increase in the temperature at boiling. If I look at this similar kind of thing going on, though, with the adjacent group where I have oxygen, sulfur, selenium, and tellurium, it's a different picture, and this water is acting like a big anomaly. So what's going on with water? Okay. In this case, we have a special case of van der Waals forces, or intermolecular forces, called hydrogen bonding. And the dipole-dipole interaction, when hydrogen is bonded to one of these, nitrogen, oxygen, or fluorine, it's unusually strong. And the way you remember which atoms are involved, or hydrogen bonding is possible, just remember ET, right, and it's phone, home, right? Phone, home. Okay. So it's unusually strong when the hydrogen is attached to a nitrogen, oxygen, or fluorine. And we call these interactions hydrogen bonding. And it arises in large part because the nitrogen, oxygen, and fluorine are all very, very electronegative. Really have a large pull on the atom, causing greater dipoles. There's also a little bit of this is that when you have one of these attracted to a hydrogen, the nucleus of the hydrogen is somewhat exposed, making it even more polar. Okay? So here's a chart that you can refer to when you're thinking about intermolecular forces.